Alright guys, we're going to go over this Chris Pratt problem that we ended with here today. This situation is going to be where there are two separate objects, so similar to the Lukey problem in that way, or the the video I just shot, or the Pelican problem, or the Climber problem. The major difference is going to be similar to the Speeder and the Popo problem. There's going to not be enough information here. So we see that Chris Pratt, blah, 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 running away. Most important things. Chris Pratt is running at a constant speed of 6 meters per second. We can see that by him saying max speed. And it says that he's got a 25-meter head start and that the Raptors start from rest and accelerate at 4 meters per second squared. So let's go ahead and get that set up over here. So let's start off with Chris Pratt. He is a, let's go Chris here. Constant velocity. So let's just go ahead and knock out constant velocity, displacement. You know what? I want to put time first here. Time, and then displacement of Chris. This is technically velocity of Chris too, but there we go. And we know that this is the 6 meters per second. Okay. And then the Raptor. Velocity initial, it said they were at rest, so that's 0 meters per second. Velocity final, we don't know. Acceleration is positive 4 meters per second squared. We don't know their time or their displacement. Oops, there we go. So similar to before, we don't have enough information. This is similar to the car and the Popo problem. We don't have enough information to solve either side. Anytime that happens, we start looking at relationships. Your key relationships are going to be time and displacement. So let's begin with time and ask this question. Do they start at the same time? Well, Chris takes off from a different spot here than the Raptor, but we're going to say they start at the same time. Then what are they going to do? Well, I shouldn't have put these numbers here, actually. So, I'm going to screw that up. Screw that up. Let's try that again. I should put them over here a little ways. This will be better. Okay, so that I can mess around with this picture a little bit easier here. All right. So what's going to happen? Chris is going to run this way. That will be the displacement of Chris. Okay, he's not going to run towards the Raptor, so you can clearly see from the picture that his displacement is not 25 meters. We don't know what it is. It's going to be somewhere over here. The Raptor, of course, to get to Chris, has to start where he is at, and boom, the Raptors is also not 25 meters. But they, of course, need to end at the same spot, so the Raptor is allowed to devour Chris. Okay? Now, do they start at the same time? I would say yes. Do they end at the same time? Well, Chris isn't going to be moving, and neither is the Raptor, because Chris is being eaten by the Raptor. So no, actually, yes, they're going to start at the same time, which means that the time of Chris is equal to the time of Raptor. So we'll just call that delta t. So it's just one variable instead of two. But displacements, this is where this picture particularly matters. Who has to travel further? The Raptor has to travel further. How much further? Well, the Raptor has to blah, 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 cover this space, which of course is 25 meters, and then he has to cover the extra space covered by Chris. So from this picture, what we get is that the displacement of Raptor is equal to the displacement of Chris plus 25 meters. Okay, now when you see something like this, it's very important that now we make sure and keep these variables separate and use subscripts. We do not want to use delta x at all anymore because there's two different delta x's. These are two entirely separate variables from one another. All right. Now the rest of this is going to be very similar to the problem before. I begin looking at Chris, because there's only one possible equation that we should be able to use because he's traveling at a constant velocity. Notice I have a subscript on the delta x, but not on the delta t, because the delta x's are different and the delta t's are not. So this is going to be delta xc is equal to 6 meters per second times delta t, and there we go. That's two of our variables. So this is one equation with two variables. So what do we need? Ideally, we need another equation with the exact same two. But usually what we would do is go to Raptor, which is what we'll do again. We're going to grab this one and grab this one. Similar to before, the equation in play is this. And that will cancel to 0, and we will get the displacement of Raptor is equal to 1/2 times 4 meters per second squared times time squared, and boom, good, Spain out. I've got two equations with two unknowns, except you don't just have two unknowns, as this displacement is not the same as that one. So we have three unknowns: displacement of Chris, displacement of Raptor, and time. So where are we going to go to possibly get the third equation? Well, we actually already have it right here. That is your third equation, your third relationship that tells the difference, tells the relationship between all three of these variables. So that is actually all we need. So kind of showing you those. Let's try to zoom out here a little bit so you can see all of those at the same time. There they are. And this is where, again, physics is technically done. Okay, you've done the work, the heavy lifting right here. Okay, but I'm going to go ahead and show the math from this particular point, but just understand that technically this setup is the bulk of what I want you to get done. Okay, so substitution. There's a whole host of ways to do this, as you have three different variables and you can solve for a bunch of different stuff. But the question on the table, if I'm not mistaken, actually, I kind of got away from that. What is the question? How far does Chris make it? Okay, so technically what we want to know is this guy right here. Now, I could go immediately for it. There's a couple ways that I could do this, but as I already have displacement of Chris solved for here, I think what's actually going to be simplest is just plugging that right in here. So instead of up in the right corner there, displacement of Chris equals 6 times delta t. So this is just going to become 6 meters per second times delta t. Okay, and displacement of Raptor here, if you look over there on the right side, is equal to 1/2 2 meters per second squared, or just 2 meters per second squared times delta t squared. Boom. This is one of those times I think that I told you, or that what's going to eventually happen, and it maybe happen quicker than some of you guys thought, in here where there's no other possible way around this. What you'll notice is that I have a t squared function, a t to the first function, and a term without a t at all, which means this is a quadratic equation and must be solved as such. So I'm going to fill this in as ax squared plus bx plus c equals 0. Already got that on one side, so I'm going to make this 2 meters per second squared times time squared. This is not on the same side, so I'm going to subtract that, minus 6 meters per second delta t. Excuse me. And same thing here, I'm going to subtract that on the other side, 25 meters equals 0. So that is A, that is B, and that is C. Now you might say to yourself, hey, maybe I'll go find, excuse me, maybe I'll go find delta x of Chris right up here, and that will solve the problem of having to use quadratic. You would be very wrong. As a matter of fact, that quadratic gets even ickier. So going over here, of course, we have negative b, so that's going to be minus the negative 6 plus or minus the square root of b squared minus 4 times a is 2 meters per second squared times c is, hold on, I don't think that's very clear, but this should be a negative right here, shouldn't it? Yes, because it should be subtracted on the other side. So that should be negative 25 meters all over 2 times a, which of course is 2 times 2 meters per second squared. Okay, now those cancel to a positive, and let me grab my calculator here. 6 squared is 36, minus 4 times 2 times negative 25. And I'll square root that whole mess. And everything inside the square root is about 15.4, and what would that be, meters per second. Okay? And when you've got a situation like this, plus or minus, for starters, if you're smart about it, you can see that if I subtract, I'm going to end up with a negative on top divided by a positive, which means I'm going to get a negative answer. So that's definitely out. But I'm going to do it real quick just to show you. Of course, there are two answers here. So I get negative 2.35. Negative time is not going to work for us. 6 plus that, 6 divided by 4, we get the correct answer of 5.34 seconds before Chris is devoured, except that is not what was asked. But it's pretty easy. It says, how far did Chris make it in that time? So all we're going to do is take that time, come right back up here, and we're going to use it right here. 6 meters per second times 5.34 seconds tells us that Chris makes it 32.04 meters. And to prove to you that this works, the weirdest zero ever, 0.4 meters, relatively works. This should not be that time. Let's see what we get out of that, though. 0.5 times 4 times 5.34 squared. Okay, this is 57.04 meters. And you'll notice those times are not the same. But the other thing that you'll notice is that they are 25 meters different from one another because the Raptors had to travel 25 more meters than Chris did before they devoured Chris right over here. There you go. Now, to put that in perspective, by the way, just in case you are chased by a raptor and you want to know how much time you have to live, well, 5 seconds is not much. You can probably figure that out. But you're going to travel 32.05 meters, which is roughly 90 feet. That's about half of the hallway outside of my room. Yeah, so yeah, Chris is not doing well. There you go. That's how you solve that.